Okay, this is classical classical electromagnetism of supposed to be, I think, September. Tomorrow is 24. That is Wednesday. We had some of you who are serving the 예비군, which is reserved army training. So I switched today's lecture to online. So I'm recording this. So we are in the middle of calculating electromagnetic field of moving charges. And last time, I remind you that what we did was to get the fields. So last time, we get the fields of charge in uniform let's use half of motion. Not sure. Let's use motion. And we did quite a bit of calculation. And the bottom line was for so we first calculated scalar potential and vector potential. And then from that, we obtained, let's say which one I want to write. Cartesian coordinate. Let me get a piece of paper first. Okay, if I write down the electric field that we obtained, which is a function of t and x, it looks a little similar to Coulomb field, except we have Lorentz boost factor appearing gamma here, and then we have x minus x0 t divided by, and here we have gamma again, and then x minus x0 t square plus there is no relativistic correction due to the boost for y and z. That's the electric field. And magnetic field associated with the electric field is simply this formula. And we discussed about 4 different implications of this result. And I'm not going to repeat this. If you're not sure, please read the text. Now today, which is 10.4, we want to calculate even more complicated. In particular, let me emphasize, we want to calculate the radiation field. We haven't talked about it yet, but we want to now consider what we call radiation field. And this is coming from accelerated charges. I'm gonna sketch through the computation and give you one homework to derive the electric field as well as magnetic field. We start with the definition of retarded time, that is this plus 1 over c, and the distance difference, which contains retarded time and position x, was the time that we normally think at the measurement point. And if I make a partial derivative on everything with respect to normal time, then we have 1 over c and round over round t r. Let's replace that to be a, which we did in the last Monday, and this is 1. Now let's work on this first on the right. So if I write round over round t over RA, let me skip the dependence on t and x. So the trick is we have 2R A, and I'm gonna do the differentiation with respect to R square, R square of A, and that's the left hand side and right hand side will be equivalent. So what that means, we have 2RA and round t. And then this whole thing is, by definition, I have x minus x0 with retarded whole thing square. So that is 1 over 2RA and round over round t on the square. So I'm gonna have x squared plus x0 is a square anyways, minus 2x dot x0. Let me put t red for now. So that's the 3 terms that we think of. Now, so this partial derivatives goes in, and we have in the denominator 2RA, but 2 factor 2 will be cancelled out, and we're gonna have let's see, trying to see if, okay, so I first want to factor out the x0 divided by dt, that's t red, and that's coming, one of them is coming from this guy, and from that I'm gonna have, and I want to also put negative sign. So let's consider this first. Then I'm gonna have 2x0 dx0 dt. And since I put negative sign in front of that, x0 will be negative at t red. And the third term is giving me minus 2x dx0 over dt. But since I already take out factor 2, I'm gonna have x. And the first term, it doesn't contribute. So that's what I have. And let's let's use this. The first term, we can say that this is R unit vector A, T, and X. And then the second term is Tx0 over dt, which is at T ret. So we can plug this result in to basically here, and I have I have actually not done this. So let's play with the last term. This is, so I want to Tx0 being evaluated with T ret. But if I do so, I have to put T ret and round T as well. This, you can say that this is V, retarded time evaluated at. And notice that we have this, and we also have this. So when we have this expression into it, we will be having round T ret over round T. And there's two of them. So we combine them, and then we'll have 1 minus R unit A T X in the product V retarded T and C because of this C, and we have 1 over. Simple mathematics, you can confirm. So that's one piece that you need to know. Now what we want to know is round I T ret. So now we want to differentiate in spatial direction on T ret. And we can also use the original definition of T ret. And let's put minus C, so that I'm gonna have, if you move this part to the right, then since I put minus, it will be plus, and round I R A. And T doesn't contribute because we are making derivative with respect to space. Now we can do the same game, meaning we have 2 RA and round I and X minus X0 T ret. I emphasize you that this is a function of T and X square. So we have 1 over 2 RA spatial derivative. We have x square plus x0 square minus 2x x0 vector. And this becomes 1 over 2r, and it's a spatial derivative. So first term does contribute to txi, to xi. Now the second term is d. Now I have to differentiate t ret first, and x0 square remains. And then I have to the partial derivative t ret. And then I'm gonna have, let me write write in this way. So I have vector 2 x0, and that is with i's component. Because simply I'm getting rid of one of these guys. And then I have also 2x. Now operation goes to x0, so I have dx0, but I need to first do it at t ret. And then I have similarly round I t ret. Little complicated, but let's look at this guy and this guy, and the second term and fourth term separately. And if you do it, you can rewrite this term and that term. It's xi minus x0, so that's r a vector, but this whole thing is divided by ra, so it's gonna be ra unit vector, but it's i's component, plus if you take a look at the second and fourth term, I have in the denominator ra as a common vector, and I have, let's take out round I t ret, which is common, and then I'm gonna have this differentiation gives me 2x0. So and 2 is cancelled with 2 in the numerator, so that gives me x0. And from the fourth term, I have x. And this one, we will write it as, again, retarded vector, velocity vector. So that's my conclusion so far. Therefore, we are saying that the final result looks like eraser. The second term is x0 minus x, so it's a minus r a, and let's change it to unit vector so that we can get rid of ra in the denominator. So I'm going to have v r t round I t ret. Why are we doing this? Well, we are doing this complicated stuff because now let's where? So we started this. Now we also calculate this, same thing, from this equation. So you no, I'm sorry. You re-express this because I have t ret as well. So let's combine the result to be similar to what we did. Now let's write down as a vector form. So I'm going to have a gradient on t ret. That's 1 over c and negative sign as overall vector. I have ra unit divided by 1 minus ra unit v r t over c. So you can immediately notice that this is what we have for this. And for gradient, we also have exactly same term, except we have different multiplicative factor for the gradient. Now, I am not going to go through this, but we are now ready to go, meaning so we are trying to get the radiation field from the accelerated charges. So it's not uniform. So we need to apply Weichard, a Lennard-Weichard potential. So we have to plug in all the calculations that we need. So in general, we need, in principle, we need black. This sort of different derivatives, and we need to know round A, round T, as well as round A with respect to get the magnetic field. But for example, for scalar round xi, we have to be first A around RA, round xi, for example. So this guy can be obtained from here. Not directly, let's write down this part is round T ret, round xi, and round T ret, round RA. And this one, this one is the one that we are gonna get from here. And this one is easy to calculate because we are making partial derivative with respect to T ret. So using this, in principle, we can get the electric field. So your homework is try to get equation number 10, 103 to 10, 105. But it's essentially one calculation. If you do it, you can express your electric field to be two component, what we call electric field velocity dependent. So let's say EV. And the other term, we want to call that to be electric field that is associated with radiation, because that's the term that you don't have it for uniformly moving charges. So now the real question is, what are these guys? I mean, the explicit form of this electric field. You need a lot of calculation to achieve this, but the answer is, it's okay. I want to make sure I am on the top. The electric field that is proportional to the velocity term, this is 4 pi epsilon 0. I have Q. Now I have RA square and RA unit minus VR over C. I have gamma square 1 minus RA unit V R over C power of 3. Okay? So observation, first of all, this is function of, obviously, of retarded velocity. Now, we have an extra term which we call electric field radiation. So we put RAD on the subscript. And this is rather complicated form, Q over RA. And what you have is VR dot cross, I have RA unit minus VR over C RA divided by, I'm going to have speed over y square 1 minus RA V R over C power of 3. And of course, B is obtained with this formula if you do it the calculation correctly. So what that means, you can also divide, it's a linear equation, so you can have B velocity dependent part and B radiation part. So I'm going to only write for you this radiation part of the magnetic field. If you use mu 0 over 4 pi, you have Q over RA, and you get rid of C square, but you will also introduce extra C square as well during the calculation. So you're gonna have, let's write down the numerator first. V R cross R over A and V dot R cross RA. So cross product makes the expression extremely complicated. Divide by C square comes in again. Okay? So let's discuss implications of this one by one. First of all, we notice that there's a difference. For velocity dependence, I have in front RA power, but power of 2, but I only have power of 1 in the denominator for the radiation. And let's take a look at where the accelerations are. The accelerations are here for electric field. And for the magnetic field, there's one typo. This is not cross product. It's inner product, but the acceleration is here for the B field, as well as here. Yes, here. So B dot. So so this first term is in the product, so it's acceleration parallel to RA unit, but the second term is a cross product, so it's related with transverse RA. So obviously, if V dot no acceleration, the whole radiation field doesn't exist. So as it should be, the radiation electric field that we defined exists only when there is non-zero acceleration. So let's keep it that way. Now, let's go back to the black color. One fact is, for non-radiative part, I mean EV and PV. PV I didn't explicitly write. You can take a look at the textbook 10.112. So EV is proportional to 1 over RA square, and same for VV. And if you think about the Poynting vector for this case, it's 1 over C times E cross V. So modulus or magnitude should behave here 1 over RA power of 4. And if you think about a small angle, which is R square A and solid angle. So at infinity, becomes 0. Meaning, if you have the surface of your fictitious sphere is large enough, then no flux is passed. So it's the electric fields and the momentum, if you want to call it that way, well, EM flux, electromagnetic flux, at the scale of very large surface of the sphere is 0. And that's why it's called non-radiative. It's contained in a large volume. But EE red is 1 over RA, and same for B red. as you can see from the expressions. So this guy can be finite. So something can go out or in from the very large surface of the sphere. So something can be radiatively moved out, and that's why it's called radiative. I can go further, but since the computations are so heavy, I'd like you to focus on your homework during your Thanksgiving, 추석 holidays, and try to derive the homework equations. And next time, I'd like to talk about radiation. We still want to talk about radiation from what we call non-relativistic charges. That's our next topic, and that will also be delivered by YouTube movie by October, I think 12th. So that's all for now. Thank you. Enjoy your holidays. Bye.